Thanks very much. Thank you very much. It's great to be back in Toronto. It's been a number of years since I was here. And I should point out that your chair, Professor Luke, and I shared an office at UC San Diego when we were postdocs together. So I'm going to tell you about quantum computing and quantum information for nuclear physics grand challenge problems. And I should point out that I am getting into this field, been in for a couple of years now, as have everybody else in the field. I got there through a sort of a circuitous route, and so let me explain that. I think it's fair to say that quantum information, quantum computing has got the potential to really disruptively change how we do research in nuclear physics and in particle physics, but across a broad host of the science domains. And I don't think that's an overstatement of the potential. So I got into this area a few years ago, initially because I was involved, as Mike said, with the NPL QCD collaboration. We have been using high-performance computing, the biggest computers that one can acquire, classical computers, to perform computations of quantum chromodynamics in an effort to rigorously derive and improve the interactions between nucleons and nuclear forces for reasons that I'll go into in a little bit. And I was involved in the DOE's efforts to quantify the amount of classical computing resources required to actually address these grand challenge problems. It resulted in a report, an Exascale report. And one of the things that stood out is when you estimated how much computing time and memory and so forth that was needed to solve the problems, there was some of the problems that were beyond Exascale. They were just off the graph that you would construct, both in memory that you required and also just the compute cycles that were required. And so then you look at what those problems are, and those problems correspond to finite density of matter. So as you increase the density of matter, the problems become more and more challenging for classical computers. They become exponentially challenging. And then also dynamical problems, so systems that involve, say, for instance, the thermalization of some non-equilibrium system. So let me start by describing some of the challenges, and then towards the end I'm going to move in to describe some of the calculations that we've been doing. These are very, very first baby steps towards thinking about quantum devices and quantum information. So one of the great things about nuclear physics is that we know exactly what the degrees of freedom are. They're quarks and gluons. We know that the forces between them, there's called quantum chromodynamics or quantum field theory. There's quantum electrodynamics, and there's also the weak interactions. And one wants to be able to start from first principles calculations of quarks and gluons and describe all the visible matter. Not only the matter itself, the structure of the matter, but also its dynamics from the various earliest moments of our universe all the way through the phase transitions, all the way through to the matter that we have today in our laboratories. So this is loosely what this picture is, and I'm biased because, of course, I've been using the technique of Lattice QCD. We want to start from first principles and move all the way to looking at the dynamics of astrophysical objects, the production of heavy elements in, for instance, explosive astrophysical environments such as supernova, and look at the dynamics, or as an example, the signals from the gravitational wave signals from the merger of neutron binaries, for instance. So one of the physics problems of the early universe is, of course, to understand the dynamics of the fundamental particles all the way from the various early moments when there's one's produced the net barrier and the matter-antimatter asymmetry, and then look at the evolution of the system through the phases. For instance, firstly, a plasma of quarks and gluons and subatomic particles, through to this recently, as in the last 10 years or so, discovered perfect fluid or near perfect fluid of these subatomic particles, all the way through to the hadrons. So if I'm looking at the QCD phase diagram, then for instance, this is temperature and this is the density of matter. So out here at approximately zero temperature, but relatively high baryon density, you have neutron stars. And then for instance, this is just temperature, and the experimental probes that we have that are operating at the moment, this diagram is probed through colliding heavy ions. For instance, you take two gold nuclei and collide them at ultra-relativistic energies. You then produce go from confined quarks and gluons into this perfect fluid, or commonly known as the quark-gluon plasma. And so there's a machine at Brookhaven, and there's the machine in Europe, the LHC, and this is Rick. And one of the goals is to look for the potential critical point. This has not been discovered, and there's a lot of effort in the US and elsewhere to try and observe this critical point of the phase diagram. And so, for instance, this is a picture of how the collisions proceed. So you have two very large, heavy nuclei, and they're moving ultra-relativistically, so they're relativistically contracted to basically sheets of particles, and these sheets come together, and near the center, of course, there's interactions, and then this produces an explosion of particles that then one reconstructs in order to understand what's actually happened during this initial collision. So we also want to look at the structure and the interactions of strongly interacting matter. So the proton, which is sort of the elementary building block, or one of the elementary building blocks of nuclei, is itself a composite particle. It's a composite particle made of massless massless particles, the gluons, and near massless particles, the quarks. And it's a highly entangled state of these subatomic particles with indefinite particle number. So you can think about highly entangled electronic states, and then you add the complication that the number of particles actually can fluctuate dramatically. And so there's been a number of Lattice QCD calculations over the last 30 years that are now reaching the precision where they're impacting experiment in an important way of, for instance, what is the spin carried by the gluons in the proton? What are the spin carried by the quarks? What is the contribution to the mass of the proton from the gluons? What is the contribution from the quarks, and so on? So this is a question. These decompositions of the structure of the proton, these are going to be answered with large-scale classical computing resources that we expect to be delivered to the field within the next several years. So this is a problem that can be solved without quantum computers. So there's other part of the experimental program at Jefferson Lab and other labs around the world, for instance, is to look at excitations of the proton. And one of those such excitations is you take the gluons and you actually excite them. And these form particles that live for a very short amount of time, but have quite different properties to what you would expect naively from just quarks alone. And then, of course, there's nuclear forces. So the nucleus is quite an amazing thing. It looks like and behaves like a collection of non-relativistic neutrons and protons whose interactions are predominantly two-body in nature. There's small three-body forces, and then it turns out that as far as four-body forces are concerned, there's no statistically significant evidence for four-body interactions. Now, as you take a nucleus and compress it as you go in deep into neutron stars, then the relative importance of the three-body forces increases, and there's other dynamics at play. So one of the questions is, and something that sort of always bugged me in studying these fields is, if the proton is a non-trivial, complicated, entangled mass of quarks and gluons, how is it the nucleus is actually so simple? Why does the nucleus look like a collection of essentially relatively weakly interacting, strongly interacting particles? So then we have, for instance, then once we have a nucleus, then there's fundamental symmetries that we can probe by the behavior of these nuclei. So for instance, one of the things that's now a high priority for research is to probe for the violation of lepton number in a universe which one can, under certain conditions, relate to the violation of baryon number. And so if one observes a nucleus changing its electric charge by 2 units without the emission of electrons, for instance, then one is without the emission of neutrinos, then one has seen the direct and unambiguous evidence for the violation of lepton number mediated by an interaction in the neutrino sector. So there's a lot of effort underway to estimate what it's going to take to reducing the uncertainties in these rates, and both on the theoretical and experimental side, there's been great progress made. There's also searches for violations of other symmetries. For instance, if nature is not invariant under motion reversal, that is, the world doesn't look the same when I run the clock forward and backward, that would indicate, in fact, that time reversal is violated, and this can manifest itself in the form of an electric dipole moment for a subatomic particle, for instance, for the neutron, and there's experiments underway to look for that. And of course, there's an associated significant amount of theoretical work to try and relate our underlying theories and potential extensions beyond the theories we know to experimental observables. Now, moving to the sort of the larger objects, nuclei in general. So if you look at this figure that I have on the right, you see a plot of our ability to calculate the properties of nuclei. And so you see, starting in 1980, one is able to calculate the properties of, for instance, the deuteron and the triton, simple nuclei, well. And then as time's gone on with the advances both in theoretical techniques, one of those being the renormalization group brought in from particle physics into nuclear many-body calculations, one's seen the size of the nuclei increase as a function of year. And then during the last period, there's been a significant growth, again with the development of new techniques, again better implementations of the renormalization group, but also the availability to the field of large-scale high-performance computing resources. And one of the things that's made such calculations possible in the United States has also been organization of the community. And I bring this up for a reason, because this is going to be related to one potential path forward in introducing quantum computation into our communities. And that is, there's been strong collaboration between people with expertise in high-performance computing, in applied mathematics, in algorithms, and in the domain sciences, close collaborations funded by the agencies that have been absolutely critical in, these teams have been absolutely critical in exploiting optimally the compute resources directed at the physics problems we're interested in. And so these projects have been in existence for, and previous incarnations now for much longer than 10 years, and they have been very successful. And one of the things that I have over here is something that's more for fun, is sort of not directly related to the mainstream argument that I'm giving here today. And what you see here is a parking garage structure, and this is that's its actual name. And what you see is the density of protons in space near the outer edges of a neutron star. And so you see that you have these flat planes, and then there's a spiral that takes you up to the next plane, and there's a spiral that takes you up to the next plane, and so forth. I think that in New Zealand these spirals go in the other direction, but but I'm not responsible for this figure. So, and what you see over here is a structure that's a parking garage structure, but this is in the biological component of a cell. And so this structure is, this is of molecules and so forth, and this is neutrons and protons. And the point is, these have the same structure, and but from very different systems. Well, what that means is the effective Hamiltonian, if you like, the effective dynamics of the components of that part of the cell, and also in the outer layers of a neutron star, are basically the same, which is fascinating. So one of the areas that's really developed enormously over the last 20 or 30 years and is accelerating is in the area of astrophysics and nuclear astrophysics. And so with the discovery of gravitational waves and now the gravitational wave observatories going from sort of discovery moving into now more and more precision in collecting large numbers of events, including the signals in the detectors as these systems merge, along with other space-based observatories over a range of wavelengths, you can now probe the structure of quite distant objects, and in particular the structure, the high-frequency components of this signal from the coalescence of two neutron stars is actually sensitive to the nuclear physics. So this is actually sensitive to just how repulsive the interaction between two neutrons is. And so in fact there's constraints now coming out of these observations that are better than what can get in the nuclear physics laboratories, which is quite remarkable. And beyond that, so from a theoretical point of view, one wants to be able to perform computations to provide input. So in fact the nuclear force is not a significant uncertainty in understanding these gravitational wave signals. So just to comment on the experimental facilities to give you an idea of the scale in the US, it's about a $1.2 billion enterprise for the construction and operation of US nuclear physics labs. And there's about 4,000 experimental users of these facilities, and they cover a range of probes. There's electron beams, there's the FRIB facility, the facility for radioactive isotope beams that's coming up. There's under construction at MSU. There's fundamental symmetry searches, as I mentioned before, for double beta decay, and so on. And of course, this is a picture of a heavy ion collision, lead on lead or gold on gold, I don't remember which. So high-performance computing has been critical to nuclear physics for a long time, and it's becoming increasingly important, both in the design and optimization of the experimental program, and this is the figures I mentioned on the previous slide, for the acquisition and handling of experimental data, and also for the large-scale simulations across a range of areas. Because basically, from the fundamental building blocks, the quarks and gluons, and all of the nuclear physics phenomena is emergent, and I'll try and explain what that means in a little bit. So in terms of our ability to calculate the dynamics of the quarks and gluons in efforts to determine the proton mass and get nuclear forces, a technique that will give you the right answer is Lattice QCD. So in this, one takes a volume of space-time, one truncates space-time into a finite volume, one then discretizes the space-time and defines a particular lattice spacing. And as long as the discretization of space-time is on a scale that's much finer than the scale of the physics you're interested in, so the errors that you make in doing that discretization are small and can be systematically removed. Similarly, as long as the volume is large compared to the physics that you're interested in, then extrapolations can be taken to infinite volume in a controlled way and to give you the predictions of the physics that you're interested in. Now, one bears in mind, because you actually have a finite lattice spacing and a finite volume, you've modified both the short distance behavior and the long distance behavior of your theory. And so this is a plot of the dispersion curve, energy versus momentum, of a single particle on such a space-time lattice. And you see that as long as the momentum is small compared to the inverse lattice spacing, then you reliably reproduce the relativistic energy-momentum relation. But then as you start probing scales set by the lattice spacing, you start to see deviations, and anything that you would calculate at the short distances, you'll get a number, but it's just the wrong number. So what this does for you is it provides a reliable mechanism to compute low energy, long distance, strong interaction quantities, but at some point, as you increase the energy and try and probe too much, it'll start giving you wrong answers. So as I mentioned before, the exascale computing needs are here. This is one example, for instance. And so what we plotted was the capacity exaflop computing. So this is basically how much cloud computing do you need. This is capability exaflop, which means so a capability system means you need the whole computer to perform your calculation, and without the whole computer, you can't do it. Whereas capacity computing means you can run a whole lot of little jobs, and the more capacity computing, the better, because you can do it in a short amount of time, but you can still do it. And so you need exascale capability and capacity computing, even just to do the three-body nuclear force, and anything beyond that from QCD to do with high precision. The precision you need is beyond exascale. And this is assuming that you have an exascale computer at your disposal running 100% of the time on your calculation, which is just never going to happen in the next 10 years. And so also the hot data versus cold data. So hot data, for instance, is is how much data do you need people to be able to access whenever they log on, and how much data is stored on tape that they can pull off if it takes a day or a week, and so forth. So it's the finite density systems and also the explicit time evolution, which are the attributes that put these problems beyond exascale. So I want to make a couple of comments before I move on to the quantum computing side of things. So when it comes to the, for instance, if I'm looking at a finite density system, what's the real problem here? And so in such calculations, one wants to calculate the expectation value of some observable, and one does that by integrating over all of the values of the quantum fields at each point in space-time, and then taking the average value of that. There's various elements to this computation that have different amounts of difficulty in performing them calculationally, but the one thing that causes the problem for classical computation, it's called the Sine problem, and there's a determinant that sits here, and this determinant at zero density is a real number, and so one can treat this as a probability distribution, but at non-zero chemical potential and non-zero baryon number finite density, this then picks up a complex phase, which averages to zero, but under statistical sampling, when the average value of that phase starts wrapping around the circle, then basically no matter how much sampling you can do, you can never recover the answer that's essentially close to zero. And so that's called the Sine problem. If you're adding e to the I theta, then you know that that averages to zero, but when you actually then do that computationally, asking of repeated sampling, what is the average value of e to the I theta? It's not zero. That's known as the Sine problem, and that plagues these computations at finite density. Similarly, in fragmentation, you have a similar difficulty. It's actually related, but less obviously so. So imagine you take a proton and a proton, and you collide them together at the Hadron Collider, and this produces a whole lot of stuff. So how it actually produces a whole lot of stuff is at fundamental level. For instance, I have electron, positron, goes to Z. This produces a quark and an antiquark. This radiates a gluon. The gluon breaks up into quark, antiquark. This also radiates particles and so on. And you get a cascade of quarks and gluons that emerge from the system in a coherent way. So firstly, the whole state is a color singlet. And so there's correlations between all these particles. The evolution involves non-trivial tracking of entanglement between these particles. And then eventually these particles then form the hadrons that enter into your detector. And so classically, one can't even begin to start to perform a real-time evolution in a quantum field theory of this type of process. You just can't keep track of the phase information along the way. It's too complex. And so this looks like a particle physics process, and it is, but when you go back to colliding nuclei, you're actually dealing with processes like this, except they're occurring in the middle of two heavy nuclei that have just collided. So then you're having fragmentation of process that looks like this, but it's in the background of other particles, and so they can interact with each other and modify the behavior that you would see in a vacuum. And so that's even more complicated. So that's this real-time evolution in a background at finite density. So back in the early 1980s, when I was at Caltech, Richard Feynman was thinking about simulating physics with computers, and I didn't pay any attention to it because it didn't mean anything to me at the time. But he had infinite wisdom, and I and many others had limited wisdom. Nothing's changed in that respect much. And so there's a beautiful paper that came out, and of course there was other people thinking about these at the time with similar things. And so this paper asked the question, can quantum systems be probabilistically simulated by a classical computer? So that's what I've been talking about. All of these are quantum systems simulated on a classical computer. And then there's a chapter before, quantum computers, universal quantum simulators. And the conclusion is basically here, there's going to be problems that you can't touch with a classical computer, and I've told you what those are, at least the ones in the critical path at the moment. But the answer to this question is those processes will likely be amenable to quantum computation with finite resources. So that's where the excitement is. Those problems that were really causing problem for us classically, if there was an ideal quantum computer available, it would be not exponentially large, it would be a finite-sized quantum computer, and it could solve those problems. So the question is how to get from here to there. So let me show you some, so how am I doing on time, Mike? Okay, thanks. Yep. So I'm going to show you a couple of slides that Dave Wicker created and showed. So he's at Microsoft. And so this demonstrates for you in a very nice figure the potential of quantum computing versus classical computing. So if you're looking at a complex molecule, and I should also say that you have faculty members and groups at this university that have far more expertise in this than I do, and I'll talk about that a bit later on, but your department and nearby departments are very strong in this area. So if you look at what it takes to simulate a molecule, for instance, example, something that looks like this, then the calculation time on a classical computer will grow exponentially as you increase the number of bodies, whereas on a quantum device, this should just grow polynomial as a function of the number of atoms. So there's going to be a vertical offset because we can look at the properties of certain molecules today on classical computers, but then eventually you're going to get to a size, and it's not that big, where classical computers will be exponentially unable to perform computations and the quantum devices will take over. And so to set the scale, for instance, 100 qubit devices can address problems in chemistry that lie beyond classical computing, and 50 qubits takes you to the size of memories of the largest computers in the world, and with a system with 300 qubits, there's more states than atoms in the universe. And so if you built if you were able to build a classical computer involving all of the atoms of the universe, you still wouldn't have the capability to span the space of 300 qubits on a quantum device, which is quite remarkable. So this is another slide from Dave Wicker. This is one of the classic examples that's shown, and it's very demonstrative. And so ferredoxin, for instance, Fe2S2, this is used in metabolic reactions. Please don't ask me the details because I don't know. So a classical algorithm, this problem's intractable to actually solve this with the precision needed. It can't be done. So then in 2012, people were interested in this problem and they developed a quantum algorithm, and that quantum algorithm would take 24 billion years on a device with of order on a device with of order 200 qubits, and 24 billion years is pretty much intractable, I would say. But then in 2015, the theorists worked on this for a number of years, improving algorithms as one does with classical computing. And so they're able to actually come up with an implementation on quantum devices that will actually run this in an hour. So you've taken a problem that's classically intractable, and then 2012 was also intractable, and now one knows how to solve this problem, i.e. get the ground state energy with a certain level of precision in about an hour on 200 ideal perfect qubits. So that's really exciting. And so now the question is, how do you actually implement that and perform those calculations? So at the same time that we became concerned about the classical costs of addressing the problems in nuclear physics, a number of technology companies, and one or two in particular, made available through the cloud quantum devices. And so this allowed the average person to actually get on very easily just by sending an email, getting on and actually running simple scripts and doing quantum operations on a simple quantum device. And so this was really is what started things, at least in the areas that I know about. And as far as the things status today, roughly, the technology companies, national labs, and universities are working to develop hardware. The technology companies are making quantum devices available for computations via the cloud. So, for instance, you can run computations on Rigetti, you can run them on IBM, you can run them on INQ. That's not cloud accessible yet, but soon to be. And the laboratories in these companies are making hardware available through collaboration. And I should add, and to add to the point that I said before, and that is that, so I told you about the problems in nuclear physics and how we realize these are problematic, but the chemists have been quite ahead of the curve in this respect. And so I would say probably 10 years ago, the chemists understood that, for the reasons that I showed you in the previous couple of slides, that one needed to take seriously quantum computation to solve the problems of importance there. And so, as I mentioned before, you have a very strong group here. I talked to Alain this morning, and I'm going to talk more tomorrow. This is a group in the chemistry department. And so this group is certainly at the cutting edge of the algorithms and the applications to a number of science domains. And I think that the nuclear physicists and the high-energy physicists will have a lot to can learn a lot from discussions with the chemists. And that's actually, those discussions are starting. So the motivation for nuclear physics, let me try and be succinct here. One is provide improvements for sensing and detection. This is something that I haven't talked about, but this is perhaps the most important thing as far as nuclear physics research goes, is that quantum information, quantum science will be able to provide significant improvements, or expected to provide significant improvements in sensing and detection. We're going to be able, they'll be used to potentially perform fully controlled large-scale simulations of quantum many-body systems in the Standard Model, and this will integrate with and complement classical computing. It's not designed to replace it. Classical computing is going to get the mass of the proton right with high precision long before quantum devices will be available to perform such a computation. So the desire is not to compete with classical computing, is to supplement and take on the problems that you actually can't solve in a classical computer. And it's important to point out that currently there's no explicitly demonstrated quantum advantage for any scientific application. And so that comment can be misinterpreted, but while there's theoretical proofs that quantum devices will be able to outperform classical devices, it's not actually been shown yet, right? So in fact, the Rigetti company is offering $1 million to any person or group that can show that they're a definite quantum advantage. So if you want to make a quick $1 million, so let me just quickly go through this because I've explained a lot of it already. So the finite density systems are typically tackled with quantum Monte Carlo, and in classical computing there's Sine problems and sampling, and the techniques used is the Schrödinger equation. As one increases the number of bodies, the Hilbert space grows exponentially. So the actual number of states that you have to consider in your computation grows exponentially with the number of particles. So classical computing, what this means is you need exponentially large resources, exponentially growing memory for large nuclei, and when it comes to the quantum computing, there's no Sine problem naively, and I may come back and talk about what that is. Real-time evolution, Hilbert space grows exponentially with the number of qubits, and so this turns into a polynomial growth with the size of the system. In the Standard Model, quantum field theories and fundamental symmetries and definite particle number, these theories contain symmetries and gauge symmetries and constraints. For classical computing, these are relatively simple to implement. In quantum computing, there's a lot of work that has to be understood how to actually do that. Real-time evolution, there's integrals over phases, there's fragmentation. And one thing that I haven't mentioned is that the transport of neutrinos in dense matter. So in a supernova explosion, there's a lot of subatomic particles one has to worry about, and one of those is neutrino transport. And so there's sort of a neutrino sphere that then eventually relaxes and the neutrinos stream through the medium and they undergo neutrino oscillations. And that again requires non-trivial maintaining and keeping the track of the phase information in the evolution of that system. Classical computing, these calculations are done in Euclidean space, which limits what you can actually do. It's very hard to examine high-lying states and inelastic collisions in Euclidean space, and so one is kind of stuck with how much of the processes of interest you can address. And there's severe limitations on real-time or inelastic processes. Quantum computing, you can actually do these things. And again, there's no Sine problem naively. let me skip that because I'm running out of time. So the elements of a quantum device are qubits, entanglement and superposition, and unitary operations and measurements. These are all basic. One can think of as a elementary particle or as composite particle with the right attributes. One treats it as a quantum particle. The entanglement's a fundamental property of quantum mechanics, which is perhaps the most bizarre feature. That is, you can have two particles that are entangled, and they can be arbitrarily far apart. And yet, by making a measurement over here, it doesn't influence, but it's reflected in what you will find on measurements over here. So the biggest difference, if you're looking at a classical computer, for instance, wrong button, sorry. So if you're looking at a classical computer, for instance, formed with 3 bits, then it can be in 8 possible states. So 0, 0, 0, 0, 0, 1, for instance. And when you perform an operation on your classical computer, then you'll change the state of this from, say, 0, 0, 0 to 0, 0, 1. The power of a quantum device is you can actually put the device in a linear combination of all of these states at once. And so when you act on it with an operation, you actually can operate on all of these states at the same time. And so you have even though the number of bits is the same, you've actually processed all of these bits at once. So instead of having to do 8 operations, you've done 1 operation, but you've acted on all the possible elements. And so as an example, one can parallel process these qubits, and I'll come back to this later on. So it was coined earlier in the year that we're in the NISQ era, and so what that means is for the foreseeable future, we're going to be in a period where there's little or no error correction in hardware or software. The quantum device is expected to have a few hundred qubits at most, and at this point in time, not many people know how to operate more than just a few qubits. And then there's technical aspects of these devices. How long does one maintain coherence between the particles? The operations that you're going to perform on these devices are imperfect. And we're going to be here for several years, and so in fact these devices in the near term are not going to be a magic bullet. They're not going to replace, at least from the nuclear physics point of view, what one can do classically. We're going to be on a path towards developing protocols and developing techniques for the day arrives when these devices do become good enough to outperform classical computings on certain quantities. And as I said, we're searching for quantum advantages. This is at very early stages. And so understanding the application of quantum to scientific applications and understanding and identifying the attributes that you want of your devices is important to be doing right now. So just as in the early days of classical computers, for instance, for Lattice QCD, dictated the architectures of some of the products coming out of IBM, one expects to see the needs to solve some of the scientific applications reflected in the actual hardware of technology that goes to market at some point in the future. So when it comes to devices, again, University of Toronto has, and this area in general has, significant expertise in putting together qubits and devices. And so there's a number of different ways, different ways is not the right way. There's a number of different physical systems that people are working on to try and make them, turn them into quantum computers. And they have quite different attributes, and it's not clear at all which of these paths is going to be successful first and then ultimately successful for the applications one needs. And this is something that I just took from a Science article from 2016. And so, for instance, people are using superconducting loops, trapped ions, one looking at quantum dots in silicon. There's efforts underway to develop a topological qubit. So this is something that would have a much lower error rate, but it's yet to actually come into existence. And then diamond vacancies. And you see that there's different, for instance, longevities. How long do they live for? Some of these qubits live for a long time, some don't. And then there's also question of how fast can you apply operations to these qubits. Some can be hit quite quickly, for instance, the superconducting loops. and then some others are slower, like trapped ion. So they have different attributes, and it's not, it's not. Each of these systems is under development, and it's not clear which is going to solve which scientific problem. Right? And it could potentially all of them will have application. It's unknown at this point. So as far as the technology companies are concerned, these are what you can get your hands on roughly. And so there's D-Wave. This is an annealing machine. It has about 2,000 superconducting qubits. Google has a chip with 72 superconducting qubits and an error rate of about 0.5%. IBM has systems with 5 through 20 qubits that you can get at through the cloud. Intel's got 49 superconducting qubits, and they're making progress in silicon. IonQ, this is a commercial company spun out from the University of Maryland, is trapped ions. They have a 53 qubit system with cloud access coming. Microsoft has no system at the moment, but they're developing topological qubits, and Rigetti has a system where you can get up to about 128. So the work that really caught my attention and took me away from what I was doing before was in 2016, came out of Europe, and it was work by Martinez et al., including Christine Mushik, who now lives up the road from you. This was a calculation on an ion system of calcium-40 ions, and what they did was they looked at a very simple field theory, one-dimensional quantum electrodynamics. And so the reason one-dimensional quantum electrodynamics is interesting is because it has many features that QCD has in 3 dimensions. So electric flux is confined. The ground state is in a non-trivial phase. It's in an antiferromagnetic phase. There's a condensate. Charges are screened, confined. And so it shares many features. It's not quantitatively similar, but qualitatively it allows you to look at a system that shares interesting features. And so what they did was they set up their system so that there was no particles present in the ground state, and then they evolved the system through the applications of lasers, and they could then calculate the number of electron-positron pairs in the system as a function of time. So this was a real-time evolution on a quantum field theory done on a quantum device. So this was that first calculation of that. And so the green curve is the theory, and the points are what you get from the experimental calculation. So this was the first time you could look at then a computer doing real-time evolution in a way that really preserved the phases. It's a small system. It's not a system reflected in nature, but it points in the direction. So as far as nuclear physics goes, the first steps were taken by a group out of Oak Ridge. This was earlier, so this was January of last year. And so they calculated the binding energy of the deuteron. So the deuteron, we know the binding energy very, very well experimentally. And phenomenological nuclear potentials, we know this. We know the binding energy very, very well also. But again, so they took the system, they determined effective interactions to put on the quantum device, and then they used VQE, or variational quantum eigensolver, to determine the ground state energy of this neutron-proton system, and they recovered within uncertainties and error bars the true ground state of the deuteron. So scientifically, this was not progress, right? But conceptually, and also leading the way for the future for multi-nucleon systems, this was a very exciting paper because it told you that you could actually take the technologies that have been developed in nuclear physics and apply them now on a quantum device. And I'm running out of time, so I'll try and tell you about a couple of other things and then quit. So there's been a number of course, since then there's been an increase in interest, of course. There was actually work done in 2007 on the theoretical side of things, looking at a stripped-down nuclear force and what you would actually do on a quantum device. So this was a very nice paper, and this was the first one that we can find of actually the application of quantum circuits to nuclear many-body problem. And so recently, so then there's other work that came out of Seattle on this was spectral combing. So one of the things that's difficult that's going to be difficult to do on a quantum device is to actually initialize the system. So if you just randomly put your fields down on a quantum device, then it's going to be in an excited state. There's going to be a lot of particles ringing around on your system, and you're really not going to be able to do anything cleanly. And so state preparation, preparing the initial configuration of your quantum device for which you can then start the calculation of the observables you're interested in, is critical. And so there's been a number of ways proposed to do this. This was a way that was slightly novel at the time, and that is one couples the quantum system you're interested in to a time-dependent heat bath. So it's kind of like a refrigerator where you run these things through avoided level crossings and eventually take a system that you're interested in, which is in some excited state. You drain out all the energy into this auxiliary state. This goes in the ground state, and this is in some excited state, and you just throw it away. So that was actually nice. It's not been implemented on devices. This was done on, just simulated on classical computers to see how it would work. This technology seems to work fine. The task now is to compare this on actual systems with other algorithms. One of the things that's difficult for nuclear physics, for instance, as I said, is real-time evolution, and this is also a problem in High-energy physics and the neutrino, in determining the properties of neutrinos. And this is the result, for instance, if you have neutrino scattering at relatively high energies on a simple many-body system, this is the response of that system. And so there are algorithms now available to systematically improve the calculability. Okay, so I want to skip and tell you in the last minute or so some of the things we've done. There's been enormous work by a significant number of groups now around the world on looking at how do you set up quantum field theories on quantum devices. The US is quite behind in this matter, I would argue. Other countries are ahead. There's been interesting work coming out of Europe and Australia in particular. There's been work coming out of Caltech, which is probably the place that was actually leading the US effort in setting up quantum field theories in around 2012, and these are a series of really nice papers. Let me skip that and skip that. And then talk about QCD. So if one takes the approaches of asking how would you actually do QCD on a lattice configuration with a Hamiltonian formulation on a quantum device, and ask just how many qubits would you need to do the most primitive implementation, then the answer is, to be comparable with computations you can do today on a classical computer, about 4 million qubits. Now, one should keep this in mind in the slide that I showed you early on about the resources required to compute the ground state energies of a complex molecule. They started off as intractable, and then 24 billion years, and then came down to about a day. So there's orders and orders of magnitude room to improve the cost resources in these calculations, and people are starting to think now hard about how do you actually best perform computations of quantum field theories on lattices. Okay, so I got about a minute, and so let me skip stuff. And so here's a computation of the real-time evolution in the Schwinger model that we performed on the IBM quantum device. And so this was published last year, and it's interesting for many reasons. So firstly, if I go back one slide, this is the computation where if you looked at how you have to evolve your quantum system, you determine all of that computation on a classical computer, and then you apply it once to a piece of quantum hardware. And these are the results of the calculation. The gray curve is the known result that you want to achieve, and the different colors correspond to different results on your quantum computer that have errors in them, and then the red points correspond to extrapolating away those errors. Just a simple polynomial extrapolation. And so one can see estimating the systematic errors certainly takes most of the resources, but one also sees the extrapolation to the physical point, if you like, actually recovers well within errors the actual result. So this was actually quite a successful calculation, and this is the quantum circuit, part of the quantum circuit that was applied. Now, if instead of doing most of the calculation on the classical device, you perform the entire calculation on the quantum device, that's equivalent to repeated applications of this Hamiltonian, then you see that one can map out part of this curve very well through extrapolation. However, at this point, one loses coherence and the device becomes classical. So in fact, if one's just relying on the quantum device to actually get you, in this case, the particle-antiparticle number density in the vacuum, then one sees you have limited capability before you flatline, basically. The quantum device decoheres. This is, of course, expected to get better and better as time goes on, but this is the state of the art as of about a year ago. So I'm going to skip that and just mention, well, yeah. So let me just conclude. So I think quantum computing and quantum information science are now entering nuclear physics and HEP in the United States, and we have a lot to learn, particularly from other areas that are ahead. There's important experimental developments that are going on, including at this university and others. There's also important algorithm developments and understanding how to use quantum devices that's also going on at this university and nearby. The United States is catching up, hopefully. Low-dimensional systems are important, and so low-dimensional lattice field theories are important for a number of reasons, and this is what we're focusing on at the moment, with an eye to obviously going to a much more complicated set of systems. And so then this is going to impact the experimental program, hopefully within the next decade. That's the plan. It's also the case that understanding lattice quantum field theories are likely to impact quantum computing also. In particular, the structures of low-dimensional field theories potentially have non-trivial impact to understand how to develop logical qubits and error correction. And also, it's interesting to look at topological configurations in such field theories. So thank you very much.